everyone, I'm Seoyoung and this work was done in collaboration with Joonseok. Today I'll be presenting our work on PoseDiff, post-conditioned multimodal diffusion model for unbounded scene synthesis from sparse inputs. NeRF models have emerged as powerful representations for novel view synthesis, demonstrating state-of-the-art performance. However, these models often hold limitations with the requirement of dense coverage of input views and expensive computations. Particularly, a lack of dense and large-scale coverage of the scene can cause practical issues in various applications, such as robotics, AR, VR, and autonomous driving, where input is often very sparse with only 1 to few views available per object or scene of interest. Various methods have been proposed to circumvent the need for dense scene coverage, but they still have their limitations. For instance, models that are first pre-trained and then fine-tuned on a test scene involve challenges in acquiring pre-trained datasets and generalizing to novel domains at test time. Methods that optimize a network for a particular scene from scratch often require additional external supervision and struggle in rendering beyond low resolution and simple scenes. Moreover, previous models that reconstruct based on sparse views especially struggle with generalizing to complex or unbounded scenes, where the camera may point at any direction of the scene with more than one scene content located at an arbitrary distance from the camera. For instance, as shown in the figure on the left, models for sparse input views such as RegNeRF find difficulty in complex scenes with high-frequency details and content in the periphery of the scene, as is shown in the top example. These models also struggle with reconstructing unbounded scenes, as shown in the bottom row. As a result, we get unclear and inconsistent floating artifacts in reconstruction. Similar observations can be found in the figure on the right with models that reconstruct unbounded scenes with dense input views, such as NeRF-360, especially when the number of input views are drastically reduced. Moreover, without the intentionally designed supervision with a deterministic inductive bias based on the main object being the center of the scene, view-based models often fail to converge to a level of photorealistic rendering. This phenomenon was especially prominent in extremely sparse scenarios, such as where there are 3 or 6 input views, even for very simple scenes, regardless of the number of training iterations as shown in the figure. Overall, it can be summarized that models still struggle to learn from the sparse information of images and poses, along with another issue with NeRF-based models, that painfully expensive and long computation times are necessary to train and inference the models. Although the results may not be favorable, as demonstrated here, it may still take up to several days to train a NeRF model for a single scene. Therefore, in order to fill in the sparse information and reduce computation times in conventional approaches to sparse view-based models, we propose to utilize the ability of diffusion models in generation based on common sense and prior knowledge. Specifically, we plan to take advantages of the generative powers in formulating plausible views and relatively shorter computation times of diffusion models, while maintaining the strength of NeRFs in modeling with 3D view, global view consistency by leveraging pose parameters from NeRF. Our model, PoseDiff, is a pose-conditioned multimodal diffusion model that generates realistic views from certain viewpoints. The diffusion model is used to augment the lack of information in sparse view scenarios and to accelerate computation times. The model is trained with 3 inputs. First, we have image latents, sampled from a diagonal Gaussian distribution encoded with VAE for each of the small number of input images, such as 3 or 6 images. Second, a tokenized embedding of a representative text prompt with a customized token to describe the target scene. And thirdly, we have corresponding camera poses processed into rays of origin and direction values per pixel for each input image. The diffusion model is optimized to refine the noise images and inputs iteratively until the ground truth image is reconstructed with the L2 reconstruction laws. As a result, the model learns the relationship between 3D camera configurations and the corresponding views in a localized latent subspace relevant to the target scene of interest. With this trained conditional multimodal diffusion model, we can now inference and synthesize realistic novel views from camera viewpoints which were previously unseen in training. Results show that our model is able to generate plausible novel views for both simple forward-facing scenes and unbounded scenes with sparse input views in much shorter computation times. In comparison to a view-based model, our model is able to render plausible novel views without floating or unnatural artifacts for all types of scenes tested with sparse inputs. And this was possible even without the injection of inductive biases. It is notable, however, that there is some trade-off between capturing high-frequency geometric details and maintaining fidelity to the color schemes of the target scene. Compared with a dense view-based model, such as NeRF-360, with extremely sparse inputs, our model succeeds to converge to a clearly renderable image at a much shorter training and inference time. With the same computational resources, our model takes several orders of magnitude less in time for training and only takes around 2/3 or a quarter of the time for inference compared to baselines. In our ablation studies, we were able to confirm the effects of the conditional inputs of our model. Firstly, using a descriptive specialized token, text tokens such as CWX, as opposed to text tokens consisting of pure ordinary natural language words, helped to generate images with less variability, targeted to the given test scene. As shown in a rough diagram on the right, specialized text tokens seem to allow learning to take place on the latent space relevant to the particular instance scene, such as a T-star T-Rex, instead of a general class that includes similar instance scenes, such as a T-Rex. Secondly, while simple text conditioning results in generation of views seen from a relatively uniform set of camera poses, the additional pose conditioning our model utilized seemed to synthesize much more realistic novel views from various camera viewpoints. Thus, we conclude that using camera pose to condition a diffusion model does help the model to understand and reason about 3D-aware camera viewpoints. To sum up, in this project we focused on the aspect that previous NeRF-based models for novel view synthesis often hold limitations with the requirement of dense scene coverage and extensive computations. Few view-based NeRF models also struggle with generalizing to complex or unbounded scenes, generating low-quality images with undesirable artifacts. In order to enhance the quality of synthesized views for unbounded scenes with a few sparse inputs, our model, PoseDiff, a pose-conditioned multimodal diffusion model, combines the fast and plausible generation ability of diffusion models and 3D-aware view consistency of pose parameters from NeRF-based models. PoseDiff renders plausible novel views while maintaining geometric details in significantly less computation times. Thank you for your attention. If you have any more questions, please come by our poster during the poster session, and we'd love to talk more about our ideas with you.